Okay, so now we're going to review for the first exam, which is covering chapters 1, 2, and 3. So we'll start by, uh, well, not chapters 36, 37, and 38. The first three chapters we covered in the course. So let's take a look at chapter 36. So this is Einstein's theory of special theory of relativity. It's what he is most known for, although he comes up quite a bit during this course. And to begin, back in at the turn of or the beginning of the 20th century, the it was assumed that there was some sort of reference frame at which the velocity of light was constant, and that um, all the other objects moved relative to that reference frame, and that it was possible to uh, determine changes in the velocity of light relative to that base reference frame. So the base reference frame was called the luminiferous ether. But the best experiment to determine uh, the Earth's speed relative to the luminiferous ether was designed by Michelson and Morley. And, it was a simple interferometer. A beam of light is split and then recombined. The path lengths were adjusted to be exactly the same. But if one of them has been moving, if they've been moving at different velocities relative to the ether, one would be shifted relative to the other and you get an interference pattern. And what Michelson and Morley showed was no matter how they configured it, how they oriented their device, they couldn't get the interference pattern. That's the velocity of light was always the same. And it's considered the most famous null result in all of physics. And because they were looking for evidence of the ether and they found none. So while Michelson and Morley were doing this, Einstein took a different approach. Um, again, the uh, physics as described by Newton and Maxwell's equations were not fully consistent with each other. Um, and they certainly weren't consistent if you allowed for the speed of light to vary. And while most people were working under the assumption that Maxwell's equations had to be adjusted to make them consistent with Newtonian physics, Einstein worked from the opposite direction. He made the assumption that, well, what if the speed of light is constant in every reference frame? So no matter how you're looking at the speed of light, you get the exact same result. And then followed where the mathematics led him, which is basically the same approach that Maxwell took to, which enabled him to draw some very profound conclusions. And so the primary consequences that are if you take the speed of light to be invariant, then space and time become relative. Um, and so special relativity is working under the special case where v is constant. There are no accelerated motions involved, and even without factoring acceleration in, acceleration comes into play with general relativity. Um, you get some consequences. Again, no absolute length, no absolute time. Events that are simultaneous in one frame of reference might not be in a different frame of reference. So the first consequence is called time dilation. So what happens is that the time interval between two events measured by an observer moving with respect to the clock is going to be longer than the time measured, or the time between the same two events measured by an observer at rest with respect to the clock. So the observer on the train that's moving at a relativistic speed sees a smaller time than the observer outside the train. Um, and so the factor involved is 1 of over the square root of 1 minus v squared over c squared, where c is the velocity of light. And so you have this ratio. And so often when we're talking about relativistic problems, you'll see the velocity expressed not in meters per second, but as a fraction of the speed of light. Often it's easier to work that way. So the time that an observer moving with respect to a clock observes is longer than the time, the time interval between two events is longer than the time interval measured by an observer that's stationary with respect to the clocks as far as measuring the same event. So that's what time dilation is. So a clock moving past this stationary observer measures time more slowly than a clock in the stationary observer's hand. And so if you're traveling in deep space close to the speed of light, and then come back to the Earth, um, you'll be quite a bit younger than your twin who stayed back on the Earth. The corollary to time dilation is length contraction, or so it follows from that that if time isn't absolute, space can't be absolute either. So let's say you have an observer O primed on a rocket ship moving with a velocity v with an observer O, relative observer O on Earth. They measure distances differently. So the length of an object moving with respect to an observer, or the distance to the object, is shorter in the direction of motion than the length measured by a stationary observer. So if you're moving towards an object, it will appear closer to you than it will to a stationary observer. And the closer you are to light, the speed of light, the closer that object will appear. And then you start to talk about, well, that's position. If position and time are relative, doesn't velocity have to be relative as well? And the answer is yes. So you talk about you develop what are called the Lorentz transformations, and which are derived with respect to um, you have an observer O prime measuring one velocity, and then what's the velocity, for a third object, and then what's the velocity observed by or measured by observer O, and so you go through all the transformations, and so you have these, you have multiple steps into getting the derivations. And what that leaves you with and what that leaves you with is uh, again, going through these steps, you have the basic Lorentz transformations, and notice you define v as essentially being the x direction. So that's the direction that O prime is moving in relative to O. And so that's considered the x direction. And then you look at a third object that could be moving in all, can have components of the velocity in all three directions. And so u primed x, u primed y, and u primed z are the velocity measurements that the observer O prime measures. And then you're measuring what O measures. And again, so these are the velocity. This is the velocity of a third object. So, but if the problem asks you for the velocity of a certain object relative to a certain other observer, then the velocity of the object it's asking for is ux, uy, and uz. The observer, the velocity that it's being measured relative to. That observer you define as observer O, and then you typically a second object um, that is observer O primed, and so you know the velocity of um, uh, you one of the objects relative to observer O primed, and so you use these equations. So ux is equal to u primed x plus v. So we're assuming v is moving in the positive x direction. Or rather, observer O primed is moving in the positive x direction relative to observer O. And so you get this factor that always shows up in the denominator, 1 plus v u primed x divided by c squared. So that's going to be in every term. And then you have uy is equal to u primed y over gamma, and uz is equal to uz primed over gamma. So there's an element of length contraction that's involved and that you need to take into consideration. So then we talked about momentum. And so we went through the derivation of this, that basically the product of mass times velocity is not conserved under relativistic conditions, but the product of gamma times mass times velocity is. So we define the relativistic momentum as gamma mv, and then with that, momentum remains an observed, rather a conserved quantity. And so that brings us to relativistic energy. And so you can derive the equation for the kinetic energy, and that it equals gamma minus 1 mc squared. And as it turns out, and this was something else that Einstein figured out, that if you have a photon that moves from point A to point B in an object, assuming momentum is conserved, the object is going to move a little bit. In order to conserve the location of the center of mass, that you must be able to treat the photon that moved as having an equivalent energy equal to mc squared. So you can, or having an equivalent mass rather equal to E over c squared. So the idea of equating energy to mc squared starts with that. And then when you get to relativistic kinetic energy, the mc squared comes into play. And so you effectively have a term where you have the total kinetic energy gamma minus m, or gamma mc squared, and you subtract from that the kinetic energy. You're left with what Einstein described as the rest energy, that's equal to mc squared. So with a couple of thought experiments, based on the direction based on what his math had taken him so far, he came up with the idea that energy was actually equal to stored mass. And this has been the most significant and experimentally verified consequence of the special theory of relativity, that every object has a rest mass equal to its mass multiplied by c squared, and so that, rather, a rest energy, and so mass as a result is stored energy. And you can express total energy in terms of the momentum, the relativistic momentum of an object. So E is equal to p squared c squared plus m squared c to the fourth, or the square root of E is. And so that's something that can be fairly easily derived. And so that's chapter 36 on special relativity. Let's then move on to chapter 37, the early quantum theory. So a lot of this was, or a decent amount of this was actually developed before Einstein, or before the special theory of relativity, excuse me. And some of it was even, developed by Einstein himself when we talk about the photoelectric effect. So Maxwell had established that light was an electromagnetic wave. And it was also determined that even though it was a wave, it exhibited particle-like qualities, and it didn't appear to have a mass per se, but it could exhibit particle-like qualities. So Allowing for electromagnetic waves to also act like particles made it possible to explain what was observed at the atomic level. And another important theoretical development was the idea that energy changes in discrete quantized steps. So there's no continuous spectrum of energy. You have to jump from one energy state to another energy state, or jump down back to a lower energy state. So the process of figuring all this out was started by Stefan, who had uh, created the law for black body radiation, and that's a general form of the law. So the total intensity emitted by a black body, which is basically an idealized object that absorbs all the radiation um, that it's in contact with, and then re-emits the radiation in order to be in balance. And so the intensity is equal to the emissivity, a number between 0 and 1, multiplied by the surface area, multiplied by sigma, which is the Stefan Boltzmann constant, multiplied by the fourth power of the Kelvin temperature. So there was a clear dependence on temperature, but the radiation also has a wavelength dependence. And Max Planck was able to explain why. I mean, a lot of bodies or a lot of objects emit radiation similarly to black bodies, and that includes the sun and the earth. That the actual spectrum is not all that different from the black body spectrum. So it has, even though it's a theoretical object, the black body, it has some important real world consequences. So Max Planck was able to explain black body radiation by assuming that the black body consisted of vibrating bodies with discrete energy states. So uh, the black body had vibrations um, of specific frequencies, and so the energy consisted of an integer multiplied by h, which is called Planck's constant, and multiplied by the frequency of the radiation. And starting with that assumption and doing the math, he came up with the radiation formula for a black body as a function of both wavelength and temperature. And it's a fairly complicated function. Although if you integrate it, you wind up getting the Stefan's law we showed in the previous graph. The one thing we're going to focus on here is that the relationship between the wavelength of peak intensity. Now, this is assuming you're expressing the intensity in terms of watts per square meter per nanometer of wavelength. It's possible to express it in terms of watts per square meter per inverse wavelength, or watts per square meter per hertz of frequency. But if you express it in terms of watts per square meter per nanometer of wavelength, you have a simple relationship between the peak wavelength and the Kelvin temperature. That product equals 2.90 times 10 to the negative 3 meters kelvins. And so you see how the law works in practice, that the intensity gets higher as it gets hotter, but the intensity spectrum shifts towards smaller wavelengths. And so the sun can be the sun's surface can be approximated at least adequately as a black body. You see, it's not a perfect correlation, but it lines up fairly closely with a black body spectrum of 5,780 kelvins. And you see there are some dips to where corresponding to where there's absorption of radiation within the solar atmosphere. But otherwise, it can be approximated fairly well, and it gives a reasonably accurate estimate of the sun's surface temperature, about 5,780 kelvins. And you can do the same thing for the Earth's surface. And so this was taken from a satellite reading over, I believe, the Sahara Desert. And so the 320 kelvins is pretty hot, but remember, it's the surface temperature. It's not necessarily the air temperature above the surface. So you have the sunlight um, landing, reaching the surface and heating up the surface. So the surface is quite a bit warmer than the air. And so that's why you have this baseline temperature of 320 kelvins, which is well over 100 degrees Fahrenheit. And you see in areas where no parts of the Earth's atmosphere absorb significant amounts of infrared radiation corresponding to those wave numbers or the frequencies, that the black body spectrum is approximated pretty well. But then you have gases that are in the atmosphere that absorb the Earth's radiation and keep it from getting into space. And so that's what the greenhouse is. So you see methane, you see water vapor, you see ozone. Where the peak of the black body radiation is, again, this is watts per square meter per inverse centimeter. So instead of per nanometer wavelength, it's per inverse centimeter per inverse wavelength. But where that's a maximum, that's where you see CO2, carbon dioxide, absorbing a lot of radiation and keeping it from getting into space, basically keeping it in the Earth's atmosphere. And that's basically what the greenhouse effect is. And you see more water vapor at wavelengths beyond that as well. And so the photoelectric effect was explained by Einstein. This is actually what he got his Nobel Prize for. It was not for special relativity. So the basic phenomenon that was observed was you can shine light on a substance and get electrons, and get a current to result. But you can stop the current if you expose the ejected electrons to a potential difference working in the opposite direction. But if you increase and so that's called the stopping potential. But if you increase the potential difference beyond that, then you start to see a current, and the current increases up to a point. So what does that mean? Well, it means there's a minimum energy that's needed to eject the electrons. And Einstein was able to explain that. So light can be treated as discrete particles called photons. A photon of light can give all its energy to an electron in the metal. And but there is a work function, which is the energy an electron needs to break free from the metal. So if the energy given to the electron by the photon does not exceed the work function, then the electron stays within the metal. It does not get ejected. But if it does exceed the work function, then you can observe the electrons being ejected, and you can observe a current being measured. So the maximum kinetic energy that a photon can have at a given frequency is equal to hf minus the work function. So only photons with a minimum frequency of the work function divided by h, or the cutoff frequency, can liberate electrons. And so the energy of the photon can be expressed as Planck's constant times the frequency, or Planck's constant times the speed of light divided by lambda, the wavelength. Remember, c is equal to f times lambda for all electromagnetic waves. And in general, the velocity of any wave is equal to the frequency of the wave multiplied by the wavelength of the wave. And the momentum of the photon is given by p is equal to Planck's constant divided by lambda, or divided by the wavelength. That brings us to the Compton effect. So what happens is you shoot X-rays into a block of graphite. The X-ray comes out at a different angle with a slightly altered wavelength, a slightly increased wavelength, which means it's lost some energy. And then an electron gets ejected in the opposite direction. And you can explain that, again, assuming light is a particle. They're treating light as a particle with momentum h over lambda. And that momentum is conserved in the x and the y direction, and kinetic energy is conserved. So there's an elastic collision. Kinetic energy is fully conserved, and you get this formula that the increase in wavelength is equal to h divided by the mass of the electron times c. If it was an object other than the electron, you would change the mass in this equation, but h and c remain the same, multiplied by, in parentheses, 1 minus the cosine of theta, where theta is the scattering angle of the photon. And so h over the mass of the electron times c is equal to 0.00243 nanometers, and it's called the Compton wavelength. But if it's possible for objects that don't have mass to behave like particles, is it also possible for objects that do have mass to behave like waves? And the answer turns out to be yes. And de Broglie made that discovery with electrons, that any matter with the momentum p has a characteristic wavelength lambda is equal to h over p, just like a photon does. And a frequency f is equal to E divided by h. And so you can create interference patterns with electrons, for example. So you can observe wave-like properties in electrons. So all this information was then put to explaining the atomic spectrum. Different elements, certainly different gases, when excited, emit different wavelengths of light. So the question becomes, why? And each substance has a characteristic spectrum, which are the wavelengths of electromagnetic radiation that that particular atom or molecule can absorb or emit. And it absorbs the same wavelengths that it emits. So, the absorption spectrum and the emission spectrum have the same wavelengths. So an atomic spectrum is not continuous, but it consists of discrete absorption or emission lines. So this is hydrogen. So you have a line in the low 400s that's violet, another line that's sort of bluish, a line that's more green, all of which are between 400 and 500 nanometers, and then another line that's red between 600 and 700. For mercury, it's a bit more complicated. For neon, it's more complicated still. And then you see the emission, or rather, that's the emission spectrum of hydrogen. Then you see the absorption spectrum. So if you have hydrogen gas and you shine light, you shine white light or sunlight into that hydrogen gas, you will see dark areas at very specific wavelengths where the radiation has been absorbed. And again, the absorption lines directly correspond to the emission lines, which are up at top. So the first explanation, or the first step to coming up with an explanation, came from Rydberg. He saw a mathematical pattern in the wavelengths of radiation of the hydrogen atom. So 1 over lambda equals a constant that became called the Rydberg constant, multiplied by 1 over m squared minus 1 over n squared, where m and n are integers. N is the greater integer and m is the lesser integer. And so it effectively said that the photon is emitted when the energy goes from a state n, or higher energy, to a state m. So Rydberg was able to see a mathematical pattern in the wavelengths. He wasn't able to come up with an equation that fit that pattern. He wasn't able to come up with an explanation why that equation worked. That explanation was the responsibility of Niels Bohr. And so we started with a few assumptions. One, the electron moves in a circular motion around the proton according to the Coulomb force. So basically, centripetal motion with the electrical force being equal to mv squared over r. Only certain orbits are stable and allowed, and the condition being that the circumference of the orbit must contain a whole number of wavelengths. So 2 pi r is equal to n lambda. And then the hydrogen atom emits radiation when the electron jumps from a higher energy state to a lower energy state. And so from that, you get the potential energy from uh, that goes back to chapter 24 in or chapter 23 in the book. The potential energy between a proton and an electron. And then from centripetal acceleration, you can figure out the kinetic energy. So the potential energy is equal to negative ke squared over r. The kinetic energy is equal to positive ke squared over 2r. So the combined energy is equal to negative ke squared over 2r. And so that's relative to zero energy and infinite distance away. So combining the de Broglie wavelength with postulate 4, the idea that 2 pi r is equal to n times lambda, lambda can also be written as h over p. So non-relativistically, you can write 2 pi r is equal to nh over mv. You can then solve that for v, and we introduce a new term h bar, which is equal to h, which is Planck's constant, divided by 2 pi. And then you can solve for the radius from that. You get the kinetic energy, and again, you can solve for that in terms of h bar, and then solve, but we already know it's equal to ke squared over 2r. So what you get is that the radius is equal to n squared h bar squared over mke squared. And basically what that's telling you is n equals 1, you have what's called the Bohr radius. That's the smallest radius the electron can have. For n equals 2, that radius is quadrupled. For n equals 3, that radius is multiplied by 9. And then you can solve for the energy in terms of n as well, that E is equal to negative mk squared e to the fourth over 2n squared h bar squared. So you have the radius in terms of the Bohr radius, which is equal to 0.0529 nanometers. The total energy in electron volts, you can get a number that's converted into electron volts divided by n squared. And so that number is equal to negative 13.6 electron volts. So if n equals 2, you're dividing that number by 4, but keep in mind you have a negative sign. So the energy of state 2 is actually greater than the energy of state 1. And so the 13.6 electron volts also corresponds to the ionization energy of the electron. So if an electron gains more than 13.6 electron volts from absorbing radiation from a photon, it is kicked out of the electron. And so n equals 1 corresponds to the ground state. And the correspondence principle says that quantum mechanics and classical mechanics should agree when the difference in energy levels is small. However, the Bohr model was limited. It only really works with 1 electron atoms. And it also turns out that there are additional energy sublevels for a given value of n. And so that was something that's observed. We will talk more about that when we get to the next chapter, so after the exam. And so you have, these are the different states that go correspond to n equals 1. So that's the Lyman series. Those are high energy. Those are in the ultraviolet. The Balmer series is what's visible in the hydrogen spectrum. And so the spectral lines in the Balmer series correspond to n equals 2. The Paschen series, which is in the infrared, and all subsequent series correspond to n equals 3. And the Balmer lines are what we can see visibly. You can detect the lines in the Lyman series with an suitable detector for ultraviolet radiation, but we cannot see the Lyman series. So that's chapter 37. And that brings us to chapter 38, which is the Schrödinger equation and quantum mechanics. So We start going back to the de Broglie wavelength. We start by developing a wave function, much like the waves in motion um, that you saw in physics 3, where a wave is a function of space and time, and it's typically some sort of sinusoidal variation. The square of the wave function enables you to determine the probability of an electron being in a specific location at a specific time. So the wave is actually related to the probability of an electron, of being at a location. And what Bohr and Werner Heisenberg concluded was that there is an actual physical limit to our ability to measure things, and measuring uh, to a greater precision than that limit is, by the laws of physics, impossible. So that limit was defined by the Heisenberg. And basically, the product of the uncertainty and momentum and the x position and x momentum, that product has to be equal or greater to h bar. Again, Planck's constant divided by 2 pi. And similarly, the uncertainty in the energy or the uncertainty in the time, the product of those uncertainties also has to be at least equal to h bar. So then you develop an equation. So Schrodinger developed a time-independent equation and a time-dependent equation that are ultimately statements of the conservation of energy. So you can think of negative h bar squared over 2m times the second derivative as being a kinetic energy operator acting on the wave function. So you have that plus the potential energy times the wave function is equal to the total energy times the wave function. So this is non-relativistic, time independent. With dependent, you need to get into complex numbers. So you have a total energy operator that's equal to I times h bar times the partial derivative with respect to time. So you have a time independent version and a time dependent version. We're going to focus on solutions to the time independent version. And so we start with free particles. So meaning there's no potential energy. So you get this differential equation, and this is readily solvable. It's equal to a times the sine of kx plus b times the cosine of kx, where k is equal to 2 pi over lambda. So that, again, that goes back to physics 3. But from the Schrodinger equation, it's also equal to the square root of 2 times the mass times the total energy, which in this case is equivalent to the kinetic energy, divided by h bar squared. And again, we're assuming non-relativistic. So now we're going to look at an infinite square well where the potential energy is infinity if x is less than 0 or greater than the width of the well, L. And then it's 0 inside of it. So the wave cannot exist outside the well. So the wave function has to equal 0 outside the well. The wave function must also be continuous. So the wave function has to equal 0 at the boundaries. So there can't be a discontinuity in the wave equation. So the wave equation has to equal 0 at the boundaries. So that creates boundary conditions that make it possible to solve the problem. So the cosine can't be 0 at x equals 0, so you can't have a cosine term. So b is equal to 0. And what about at x is equal to L? Well, what it turns out is that that's solvable provided that the product k times L is equal to an integer times pi. So that would make it possible to solve for the wave function. So what that's telling you is that you have quantized states in this infinite square well. And so K is equal to N times pi over L, which we can then solve for the energy. So you have quantized energy states where E is equal to N squared H squared over 8mL squared. So this is the energy of an electron in an infinite square well. And so the lowest possible state is N equals 1. That's called the ground state. The N equals 2 state has 4 times as much energy as the N equals 1 state. The N equals 3 state has 9 times as much energy as the ground state. And you can solve for A, the constant A, using the normalization condition, so that the wave function squared integrated over from negative infinity to positive infinity, which in the case of the infinite square well is from 0 to L, that integral has to equal 1. So, the probability of it being somewhere is 1, is what that means. And so with that, you do the integration and you solve for A. It's equal to the square root of 2 divided by L. And so that makes it possible, again, to assess the probability of an object in a given state being at a given location. So then we move from the infinite well to the finite well. And so you have a potential energy U naught outside of the well and U inside of it. In classical mechanics, if the total energy were less than of the electron were less than U naught, it couldn't escape the well, but it can in quantum mechanics. And so solving for this wave equation, in order to solve for this wave equation, you need continuity not just of the wave function, but also its first derivative. And so again, that makes it possible to solve the wave equation. So inside the region, you've got a sinusoidal function, but it doesn't go to 0 at the boundaries. So you can't assume anything about A and B from that. You can't assume B is 0. But if U is greater than E, you can solve for the wave function similarly to what we did before, defining G squared as being equal to 2m U minus E divided by H bar squared. And then, so you have a sine function inside the well, and then outside the well, you have exponentially decreasing functions. So e to the gx when x is negative. So it's going to be exponentially decreasing as you move to the left of the well. And then to the right of the well, you have, again, a constant times e to the negative g over x. And so these are how the wave functions look. So again, the first derivative and the function itself have to be continuous at the boundaries. And so again, that makes it possible to solve for the wave functions. And so for n equals 1, you have a peak in the middle, and then it goes down to 0 past the boundary. For psi 2, it starts to go up to the left of the well, then it has a peak, then it goes back down below 0 and becomes negative, has a minimum, and then starts to come back up. But again, exponentially decaying to 0. Then for psi 3, it goes up, it peaks, it goes down, becomes negative, has a minimum, becomes up, and becomes positive again. So there are 3 extreme values. And then it decays back down to 0 once it gets past the well. So for a given wave function, it has a number of total maximum or minimum equal to n, is what that means. And then you can see from the probability distribution where you can find the particle in the well. And it can cross, it can penetrate the boundary of the well, but only to a certain distance, right? Because, again, the probability decays exponentially. Okay. I apologize. I had to pause for a little bit there. So you can see how the wave functions work, and then how the corresponding probability functions work. And um, we don't go into the full details of deriving these equations here. So if you take an advanced modern physics or quantum mechanics class, you will. And so what happens when E is greater than the or so the potential energy is, or rather the total energy is greater than the potential energy. So you have the um you have the wave function. So now you have uh exponentially decaying functions, but they're different because of the they're different because of the fact that E is now greater than um, the potential energy. And the particle's wavelength changes depending on the region. So you have a different wavelength in between than you do on the outsides. And so you see you have a longer wavelength outside because corresponding to less kinetic energy than you do in the middle. And uh, so the wavelength depends on momentum, but momentum goes up and down more or less with kinetic energy, or kinetic energy goes up with the square of momentum in non-relativistic mechanics. So as the momentum goes up, the wavelength, or rather, as the momentum goes up, the wavelength goes down, which is what you see inside the well. And then as the momentum goes down, the wavelength goes up. You get longer wavelengths outside the well. And then we talked about barrier penetration or tunneling. So you have, instead of a particle inside the well, or rather, high potential energy values to the left of the well and to the right of the well, here you have a barrier of width L. And so the potential energy outside the barrier is zero, and inside the barrier is U naught. And relativistic mechanics says that, or rather, in not relativistic, classical mechanics says that um, a particle can't cross through the barrier if its total energy is less than the potential energy of that barrier. But in quantum mechanics, it is allowed. And so, again, the wave function and the first derivative have to be continuous at the boundaries. And so, what you have is that uh, the wave function is sinusoidal on either side of the barrier, but exponential within the barrier. So, within the barrier, you start to have an exponential decay. But as long as the barrier is relatively thin, it doesn't go down to zero, meaning the probability of continuing further doesn't go down to zero. And as long as the probability is non-zero, or as long as the wave function is non-zero at the edge of the, or at the outer edge of the barrier, it's possible for a particle to get through. So we define G again as being equal to the square root of 2m times the difference in the potential energy and the total energy divided by h bar squared. And so the transmission coefficient, or the percentage of particles that get to the barrier that wind up crossing, is approximately equal to a to the negative 2gl. And so there are some real life examples where some version of tunneling does exist. The most obvious example being alpha decay. Some radioactive substances have, emit a proton and a neutron together, that basically escape the nucleus and uh, break the attraction, or escape the attraction from the strong nuclear force, and escape the nucleus and escape the atom. So that happens. You can also have a diode, or what's called a tunnodiode, where you have two semiconductors that are separated by a barrier, but some of the electrons pass through the tunnel diode and get to the other side. And then you can have what's called a scanning tunneling electron microscope, where the electrons jump through a space between the specimen and the microscope, and then can give information about whatever structure is being scanned. So there are some real examples of tunneling and some practical ways, some ways to exploit the possibility of quantum tunneling. And so this is how the wave function looks. So it's sinusoidal outside the barrier. You get to the barrier, it becomes exponentially decaying. And then you get to the other side and it's sinusoidal again, but there's a much smaller amplitude in the wave function, which basically means there's a much lower probability of finding the electron or whatever other particle on this side of the uh, barrier than there is on the other side of the barrier. And so that's basically what's meant by barrier penetration. So again, we're not going to get into a full-blown mathematical analysis, but you can see how the probability function looks, how the wave function looks. And again, the probability function, you're just squaring the wave function. So you still get an exponentially decreasing function. And again, smaller probability on the right side of the barrier, on the cross side of the barrier, as opposed to the incident side of the barrier. And so that's it for this chapter, and that's it for the material we're reviewing for the exam. If you have any questions about a concept or about a problem, you can reach me via email or come to one of my office hours. Otherwise, Friday morning in the Zoom room, at 8 o'clock. So I have to move things again. And again, thank you for your flexibility as far as this goes. And otherwise, so I'll see you Friday. And then don't forget, Friday at 12 o'clock, we'll meet in person in the lab. Okay, so thank you for now. And like I said, if you have any questions, you can email me or come to one of my office hours.